Okay, so I'll start with the motivation. Okay, so in this slide, you see, so in the previous days in this school, you have seen many interesting architectures. In particular, in this slide, you see two of them. On the left, we have the multi-layer perceptron, so MLP. And on the right, you see a convolutional neural network, so a CNN. And you have seen how an MLP is really an effective way to approximate very complex functions with very good results. And also, you have seen how we can use CNN if we have images to get very good results, for example, for object detection. And based on this idea that we have one filter that we can slide over the image. But in this presentation, and actually in the following two presentations, we will focus on a particular class of problems where we can, where the data for this problem can be shaped as a sequence. And that means that we have a sequence of elements. The order between these elements is important. It's one information that we want to consider. And also, these sequences, they can have variable size. So I can have a different number of elements in these sequences. To give you a quick example about this, you can think of a spam filter. So you know the problem with spam filter. I want to classify the email as spam or not. And the input is text. So it's a sequence of words. And obviously, the order between these words is important. That's the first point. And the second one is that if I have two different emails, most probably they will end up having a different number of words. So you see that if we build a system to solve this problem, we need to be robust with respect to this aspect. Let's see what happens if we try to use the architecture that I mentioned in this slide, MLP and CNN, to solve this problem. So the problem with MLP is that an MLP has a strong fixed size. So let's see at the example on the left. Like here, you see that I'm trying to build a classifier. Maybe it's this spam classifier that I mentioned before. You see that the input is this sentence, "How are you today?" So there are 4 words. And this actually can be done. It can work. The MLP can learn this. But you see that when I move on the right, in the example on the right, I have the same MLP. But the number of words now is different because we said that we don't know how many words we will have in the input. And in this case, the MLP cannot work just because the number of inputs in this architecture is fixed. I only have 4 in this particular case. And obviously, I cannot change that dynamically. And the intuition for this comes from day number 2 when you saw this architecture, and you saw that every layer is basically represented by a matrix that are the parameters. This matrix will tell me how many inputs I have and how many outputs I have. And obviously, the dimension of this matrix is fixed, so I cannot change that on the fly. So you see why an MLP cannot work in this particular way. But actually, there are some techniques to make it work. Here I'll mention one, the bag of words. And actually, we will go more in detail about this in the 3rd presentation, the natural language processing one. And this technique will allow this sequence with variable size to be represented as an input with fixed size. So it will work with the MLP. But all these techniques, they come with some disadvantages. In particular, in the bag of words, we lose the order of the element, which is really something which is really an important information when dealing with text. So we want to keep this. Ideally, we would like to keep this information. So we can say that we don't want to use MLP with sequences. Let's see what happens if we try to use CNN. So with CNN, I think it's more interesting because, as you saw yesterday, CNN can actually work on one-dimensional data. So ideally, they could work on a sequence. Yesterday, you saw most of the example. It was an image, so 2-dimension, and you saw the filter was a 2-dimension, a matrix. But you can actually make it work in 1 dimension, and the filter will become just 1-dimensional as well. The problem, if we try to do that, is that in this kind of task that we want to solve, we want to capture information from all the elements in the sequence. Like you can see the example here in the slide at the bottom. So we have the sentence, hello, how are you today? And let's see we try to run an RNN on this sequence. In this example, I chose a filter size of 3. So you see I can slide my filter and I get this output. But the problem is that there are some words that are never under the same filter. So I will never capture the relationship between these words. Like one example here is hello, the first word, and today at the end. You see that it's never in the same filter. There is actually an easy solution to this, which is to add more layers to this architecture. So now, if you remember for yesterday, we can increase the receptive field of the CNN just by increasing the number of layers. So at this point, the problem here will be solved because you see that the output A, the one on top, has a receptive field that includes all the words, all the elements in this sequence. So it can work this way, but the problem again is that we don't know how big the sequence will be. And I can have an example like this. So even if I add 2 layers now, you see that just because I added another element to my sequence, so I need to slide one more step, you see that now I end up on the top level with 2 elements. And again, I have this problem that there is not one element that is capturing all the relationship from all the elements just because the receptive field is too small for this sequence. And obviously, once you decide how big is your filter size and how many layers you have, you define your receptive field. And this means that you can always find a sequence that is bigger than that. So that's why we can use CNN, yes, but they come with these disadvantages. And ideally, we would like to find a system that is more robust, that is able to extract all the information from all the sequence.